So today we will learn about Poisson's equation. Let us start with Maxwell's first equation, which tells us that the divergence of the electric field is equal to rho by epsilon naught. This is the electric field, and this is our charge density. And we have Maxwell's third equation, which tells us that the curl of the electric field is 0. Here we have made the following assumptions: that there are no moving charges, which means we are in the realm of electrostatics. And of course, there are no dielectrics for the time being. Let us keep things simple. So, we might remember that the curl of the gradient of a scalar function is 0, and using this in the third Maxwell's equation, we can say that the electric field is the gradient of a scalar potential, which we call the electric potential or the scalar potential. And this negative sign is a convention. So using this in Maxwell's first equation, you can say that the divergence of the gradient of the electric potential is this, and this can be simplified to give us a second order differential equation, which we call Poisson's equation. This operator is called the Laplacian, and in Cartesian coordinates, the Laplacian is simply the sum of the double derivatives in the coordinates. And this actually tells us why the Poisson's equation is a second order partial differential equation, and it also shows that analytically it is not easy to solve. However, we will specify some conditions and some specific problems, and we will see how we can solve the Poisson's equation in those specific cases. So let us set up our problem. Let's say we have a closed volume V, and the surface that encloses the volume is called S. Now in our problem, the charge density inside V, that is for all points in V, is given to us. Now this is not sufficient to uniquely solve the Poisson's equation. We also need either one of the following two. Let's say we know the potential on the surface S for all points on the surface S, or we know its gradient, which is equivalent to knowing the electric field on the surface S. So we need either of these two, or let's say, to be more specific, any one of these two. So with these two information, we can find a unique solution phi for Poisson's equation. In V, which means using the charge density in V and either of these two, that is the potential on the surface or the electric field on the surface, we can uniquely determine phi, the electric potential, in all points inside V. Alright? Now, there might be charges present outside this volume. Alright? Now, these charges will affect the electric potential at some point inside the volume, apart from, of course, the charge density inside the volume. Now, the entire information of this is contained in either of these two. Thus, collectively, they can help us find the potential inside the volume. Now, any one of these two conditions along with this is sufficient. This first condition is called the Neumann, it's called the Dirichlet boundary condition, and the second one is called the Neumann boundary condition. Right? Now we will learn to solve these kind of problems using something called Green's functions, which is one of the methods for solving such problems. So let us recap. We learned something called Poisson's equation, which relates the scalar potential or electric potential with the charge density. Now this equation is a second order differential equation and is not easy to solve for any general rho or any arbitrary rho. So we set up some very specific problems that we will try to solve. In our problem, we have some volume V and it is enclosed by a surface S. We would like to find the electric potential inside the volume for all points inside the volume. For this, we will require the charge density inside the volume and the potential on the surface or the electric field on the surface, and these two boundary conditions are called the Dirichlet boundary condition and the Neumann boundary condition. And using this, we can uniquely determine the vector potential, the scalar potential in Poisson's equation for all points inside V. And we will learn one method of solving these problems called the Green's functions.